In the previous lecture, I have introduced some special discrete distributions, and in fact, three of the distributions were related to the Bernoullian trials, that is binomial distribution, geometric and negative binomial distributions. Then I introduced a concept of Poisson process, and the distribution is obtained through a limiting process by setting up the differential equations. Now, I will introduce certain special continuous distributions. The first one of them is known as the exponential or negative exponential distribution. So, let us go back to our earlier discussion. I have introduced a Poisson process. So, let us consider. Now, if you remember the Poisson process, we had a parameter called alpha there, which was actually the constant of proportionality. That means, we said that probability of a single occurrence during a small time interval is proportional to the length of the time interval. So, we wrote that if the interval is of length h, then the probability of one occurrence in that interval is equal to something like alpha h. So, this alpha is the constant of proportionality, that is called the rate of the Poisson process, or the rate of arrival or rate of occurrence in a Poisson process. So, consider a Poisson process with rate say alpha. Okay. Now, of course, this alpha has to be positive. Let us consider, let x x we have already used the notation for the number of occurrences. So, let us use another notation, let y be the time till the first occurrence. So, starting from time 0. That means, we start observing a Poisson process and we wait till the first occurrence is observed, and we denote. So, this is the Poisson process here, this is the time 0 and this is the time y, where the first occurrence has occurred. That means, between 0 to y there is no occurrence. Now, naturally this y is different than the number of occurrences. The number of occurrences is a discrete random variable, because it was taking values 0, 1, 2 and so on. Now, we are looking at the time. So, y is the continuous random variable. Now, let us find out the distribution of, what is the distribution of y. So, let us look at say probability of y greater than say small y, that is equal to probability of x y is equal to 0, because if y is greater than y, that means there is no occurrence in the interval 0 to y, which is equivalent to x y is equal to 0. Now, what is the distribution of x y? That is the Poisson distribution with parameter alpha y. So, this is becoming e to the power minus alpha y. Of course, this is for y greater than 0. If y is less than 0, then this will be equal to 1. So, if we consider the cumulative distribution function of y, that is 1 minus probability y greater than y, then it is equal to 0 for y less than or equal to 0. It is equal to 1 minus e to the power minus alpha y for y greater than 0. Now, in the case of continuous random variable, if we differentiate the cumulative distribution function, we will get the probability density function. So, we get differentiating capital F with respect to y, we get the probability density function of y. So, that is equal to then f y y is equal to alpha e to the power minus alpha y for y greater than 0, it is 0 for y less than or equal to 0. So, this is called the exponential, and since there is exponent as a negative term, this is actually called a negative exponential distribution. The moment structure of this is quite simple. If we can write down mu k prime, that is expectation of y to the power k, that is equal to y to the power k alpha e to the power minus alpha y d y from 0 to infinity. Now, this is nothing but a gamma function. So, the value is simply equal to k factorial divided by alpha to the power k for k equal to 1, 2 and so on. So, we get the mean, that is equal to 1 by alpha. Let us look at the physical interpretation of this. If the Poisson process has the arrival rate alpha, that is the rate of occurrence is alpha, then the waiting time for the first occurrence is 1 by alpha. So, it is something like saying that you can say rate is 1 in 3 minutes. So, the waiting time then will be 3 minutes for the first occurrence, the expected waiting time. Let us consider say mu 2 prime, then that will become 2 by alpha square, and therefore, variance of y, that will be equal to 2 by alpha square minus 1 by alpha square, that is equal to 1 by alpha square. So, in the case of exponential distribution, the variance is square of the mean. One may also calculate, of course, plotting of this distribution is very simple, because alpha e to the power minus alpha y, at y is equal to 0, the value is equal to alpha, and thereafter, because e to the power minus alpha y is a decreasing function. So, it will decrease. So, this is the naturally you can see this is a skewed distribution, positively skewed distribution. We can actually calculate mu 3, that is 2 by alpha cube, and mu 4 is equal to 9 by alpha to the power 4. So, the measure of skewness, that is equal to 2 by alpha cube divided by 1 by alpha cube, that is equal to 2, which is positive. So, it is always positively skewed. In fact, this is free from the parameter alpha. Similarly, if you look at beta 2, that is a measure of kurtosis, 9 by alpha to the power 4 divided by 1 by alpha to the power 4 minus 3, that is equal to 6, that is also positive. So, the peak is higher than the normal peak that we are having for the exponential distribution. Now, like the geometric distribution, this exponential distribution is also having a property which is called the memoryless property of the exponential distribution. Memoryless property of exponential distribution. Let us consider say probability of y greater than say s plus t. Then naturally, this is equal to e to the power minus alpha s plus t. If we consider probability of y greater than s plus t given y is greater than say t, that is equal to probability of y greater than s plus t intersection y greater than t divided by probability y greater than t, that is equal to probability of y greater than s plus t divided by probability y greater than t, because in the numerator this event is a subset of this event. Now, according to the formula that we have, it will be equal to e to the power minus alpha s plus t divided by e to the power minus alpha t, that is equal to e to the power minus alpha t, alpha s. Now, this is nothing but probability of y greater than s. So, what we have proved? That probability of y greater than s is same as probability of y greater than s plus t given y is equal to greater than t. Now, the right hand side denotes that the waiting time is more than s. That means, starting from time 0, that means, when we are starting to observe the Poisson process, the probability of first occurrence not being there till time s. And this one, if you look at, this is starting from time t, because till time t the first occurrence is not there. What is the probability that we need additional s time, because it is going up to s plus t. It is the same as starting from 0. That means, the starting point does not matter. This is called the memoryless property of the exponential distribution. We also calculate the moment generating function of the exponential distribution here. It is e to the power t y e to the power that will become alpha by alpha minus t for t less than alpha. Many times in the Poisson process, we do not start from the time 0, rather we start from a non-negative time alpha or time a, for example. Now, this is something like suppose we are considering any process, or say a machine is working and we are looking for the failure, that is when the system will fail. Now, the system may fail at any time. However, at many times there is a hidden guarantee given that it will not fail before a given time, say 1 hour, it will not fail before 1 month, or it will not fail before 1 year. When we purchase a product, there is a guarantee given there, and therefore, the distribution point will be starting after that. So, this is known as a shifted exponential distribution. Shifted exponential distribution. So, here we can write the distribution as, say, I am writing a more general form, 1 by sigma e to the power x y minus mu by sigma, where y is greater than mu, and here of course, sigma is positive. So, whatever moments of y were there, the same thing will be true for moments of y minus mu. That means, in general we will have expectation of y minus mu to the power k equal to k factorial into sigma to the power k. So, for example, expectation of y will become mu plus sigma, variance will become twice sigma square. Let me give an example of exponential distribution here. A small industrial unit has 20 machines whose lifetimes are independent, exponentially distributed with mean 100 months. If all machines are under use at a time, find the probability that even after 200 months at least 2 machines are working. So, let us consider, say x is the lifetime in months of a machine. Okay. Then it is given that x follows exponential distribution with parameter, that is mean is so here alpha is equal to 1 by 100, that is mean is 100, because in the exponential distribution the mean was 1 by alpha. So, alpha is equal to 1 by 100 because the mean is 100 here. So, what is the probability that machine is working up to after 200 months? So, it is probability x greater than 200. So, in the exponential distribution we have seen it is equal to e to the power minus alpha y. So, it is equal to e to the power minus 200 by 100, that is equal to e to the power minus 2. Now, let us define another random variable. Y is the number of machines working after 200 months. Then y will follow binomial 20 e to the power minus 2. So, we want that at least 2 machines are working. So, probability y greater than or equal to, that is equal to 1 minus probability y is equal to 0 and probability y is equal to 1. So, based on this binomial distribution we can evaluate it, it turns out to be 0.7746, because this is equal to actually 20 C 0 e to the power minus 2 to the power 0, actually 1 minus e to the power minus 2 to the power 20 minus 20 C 1 e to the power minus 2, 1 minus e to the power minus 2 to the power 19. So, after evaluation this value turns out to be this. Now, in a Poisson process, in place of the first occurrence we observe rth occurrence. Once again it is a generalization, like in the Bernoullian trials, in place of the first success we look at the first time rth success is observed. So, in a similar way, suppose in a Poisson process with rate lambda, rate alpha, let say z denote the time till the rth occurrence. Then we want the distribution of z. What is the distribution of z? So, we again consider in the similar way as probability z greater than z, that is equal to. Now, in a Poisson process, see this is the time z, till this time r occurrences have not occurred, that is rth occurrence is occurring after this. That means, within this portion not more than r minus 1 occurrences will take place. So, this is equal to probability of x z less than or equal to r minus 1. So, this is equal to e to the power minus alpha z to the power j by j factorial summation j is equal to 0 to r minus 1. Of course, here z has to be positive. If z is negative, then this probability is going to be 1. So, the cumulative distribution function of z then turns out to be 0 for z less than or equal to 0. It is equal to 1 minus sigma j is equal to 0 to r minus 1 e to the power minus alpha z to the power j by j factorial for z greater than 0. So, if we differentiate this cumulative distribution function, we will get the probability density function of the this random variable z. So, differentiating capital F with respect to z, we get the PDF of z as f z. Now, you look at these terms here, this contains r terms and each term has a product e to the power minus alpha z to the power j. So, when you differentiate you will get two terms at each time. So, we write it in a sequential fashion. So, it is equal to 1 minus d by dz e to the power minus alpha z plus alpha z into e to the power minus alpha z plus alpha z square by 2 factorial e to the power minus alpha z and so on plus alpha z to the power r minus 1 e to the power minus alpha z by r minus 1 factorial. So, this is equal to 1 minus. Now, if we differentiate this we get minus alpha e to the power minus alpha z. If we differentiate this one, the first term if I differentiate I will get alpha. So, I get plus alpha e to the power minus alpha z, and notice here that this term is same as this term and they cancel out. When you differentiate this you will get minus alpha square z e to the power minus alpha z. Here you get alpha square z square. So, when you differentiate you will get twice and this twice will cancel with this. So, you will get plus alpha square z e to the power minus alpha z. Once again notice that this term and this term are the same with different signs. So, they will get cancel out. So, like that all the successive terms will cancel out each other and we will be left with the last term, that is equal to minus alpha to the power r z to the power r minus 1 e to the power minus alpha z by r minus 1 factorial. So, this is equal to alpha r divided by r minus 1 factorial, which we write as gamma r e to the power minus alpha z z to the power r minus 1. Here z is positive. This is known as Erlang or gamma distribution. So, a gamma distribution has been derived as the waiting time till the rth occurrence in a Poisson process. If you notice the integral of this, because it is a gamma function, it will become 1. But you notice here that when we have derived this distribution, I have considered r to be an integer. But even if r is any positive real number, this distributional form is valid. Therefore, a generalized form of the gamma distribution will be when r is any positive real number here. Now, the moment structure of the gamma distribution is quite simple, because it will use the moments the gamma function here. Let me give the expressions for the moment structure here. We will have expectation of z to the power k as equal to r into r plus 1 and so on up to r plus k minus 1 divided by alpha to the power k. Expectation of z then turns out to be r by alpha, variance of z will be equal to r by alpha square, and in general it is a positively skewed distribution. The moment generating function of z will be equal to alpha by alpha minus t to the power r for t less than alpha. Notice here the moment generating function of the exponential distribution was alpha by alpha minus t, and this is power r. So, that immediately suggests that the sum of independent exponential variables will be gamma. Let me write this additive property, that let x 1, x 2, x r be IID exponential alpha variables, then sigma x I is equal to 1 to r, that is equal to y, that will follow a gamma distribution with parameters r and alpha. Once again this can be explained in a physical setting. X 1 can be considered as the waiting time for the first occurrence in a Poisson process. X 2 can be observed as a number of first occurrence in a Poisson process. X r can be considered as the waiting time for the first occurrence in a Poisson process. Now, if you consider x 1 plus x 2 plus x r, then you are looking at the time between 0 to t. So, it will become the first time rth occurrence in a Poisson process, and therefore, this will become simply the gamma distribution. So, that is also confirmed by the MGF approach or the moment generating function calculations that one can do here. Let me give an example here. The time to failure of a certain system has a gamma distribution with a mean of 20 days and standard deviation 10 days. Find the probability of a failure within 15 days of the start of operations. So, here we are having r by alpha, that is equal to 20, because mean of a gamma distribution is r by alpha. The variance is 100, variance of a gamma is r by alpha square, that is 100. So, if I take the ratio here, I get here alpha is equal to, this implies alpha is equal to 1 by 5 and r will be equal to 4. So, the distribution of this random variable will become alpha to the power r, that is 1 by 5 to the power 4 gamma 4 e to the power minus x by 5 x to the power 4 minus 1, that is 3 for x greater than 0. So, this is the distribution here. We wanted the probability of the system failing within 15 days. So, that is equal to 1 minus probability x greater than 15, that is equal to 1 minus integral 15 to infinity 1 by 5 . Now, in this one we can substitute x by 5 is equal to say y, then it will give 1 minus 3 to infinity e to the power minus y cube and 1 by gamma 4 dy. Now, this can be evaluated using integration by parts, actually it is an incomplete gamma function and the value turns out to be 0.3528. Now, this also suggests that if alpha is common, the gamma distributions also add to another gamma variable. Suppose we have gamma r 1 alpha and gamma r 2 alpha independent variables, then if we add them, then that will be having gamma r 1 plus r 2 alpha. Now, we proceed to another important distribution, that is the normal distribution. A continuous random variable x is said to have a normal distribution with parameters mu and sigma square if it has probability density function given by 1 by sigma root 2 pi e to the power minus 1 by 2 sigma square x minus mu square. Here x is any real number, mu is any real number and sigma is a positive real number. Now, first of all let us look at the properties of this distribution and then I will explain how the distribution is obtained in the physical situations. Let us firstly consider whether it is a valid probability density function. So, we have 1 by sigma root 2 pi e to the power minus 1 by 2 sigma square x minus mu square dx. Let us substitute x minus mu by sigma is equal to say z, that is 1 by sigma dx is equal to dz. This is from minus infinity to infinity. When the range of x is from minus infinity to infinity, sigma is positive, therefore, z will also vary from minus infinity to infinity. So, this will become equal to minus infinity to infinity 1 by root 2 pi e to the power minus z square by 2 dz. Now, notice here this function is an even function and this integral is a convergent improper integral. So, this becomes 2 times 0 to infinity 1 by root 2 pi e to the power minus z square by 2 dz. Now, in this region I can make a substitution z square by 2 is equal to say t, that is z is equal to 2 t to the power half or dz is equal to 1 by root 2 t dt. So, this integral then turns out to be twice integral 0 to infinity 1 by root 2 pi e to the power minus t 1 by root 2 t dt. Now, this you simplify, this is turning out to be simply 1 by root pi 0 to infinity t to the power half minus 1 e to the power minus t dt. This is nothing but gamma half. Now, gamma half is root pi. So, this cancels out, you get 1. So, this is a valid probability density function. Now, what I have also described during this process is a procedure for solving the integrals which involve this probability density function of this form. So, we generally make this kind of transformations, that is x minus mu by sigma is equal to z and z square by 2 is equal to t. Now, let me give you the moment structure of the normal distribution. Let us consider expectation of say x minus mu to the power say r, then that is equal to integral of x minus mu to the power r 1 by sigma root 2 pi e to the power minus 1 by 2 sigma square x minus mu square dx. Now, I will not be considering this transformation again and again, I will be just substituting this value, that is x minus mu by sigma is equal to z and 1 by sigma dx is equal to dz and then z square by 2 is equal to t. So, if we carry out this transformation, this will become sigma to the power r by root 2 pi, because x minus mu by sigma is equal to z. So, x minus mu is equal to sigma z. So, this becomes sigma to the power r z to the power r e to the power minus z square by 2 dz minus infinity to infinity. Immediately you can notice here that whenever r is an odd integer, this value is going to be 0. So, if r is equal to of the form 2 m plus 1 for m is equal to 0, 1, 2 and so on, then I will get expectation of x minus mu to the power 2 m plus 1 is equal to 0. That means, in particular if I write m is equal to 0, I get expectation of x minus mu is equal to 0. That means, expectation of x is equal to mu. That means, mu is denoting the mean of the normal distribution. That is the parameter which I specified as mu while defining the normal distribution is actually the mean of this distribution. And therefore, this expression represents central moments. So, what we have proved that all odd ordered central moments of a normal distribution vanish. Now, when r is equal to of the form 2 m, then this expression can be simplified as say sigma to the power 2 m. So, now then this expression becomes simply mu of 2 m, because it is the 2mth central moment root 2 pi minus infinity to infinity z to the power 2m e to the power minus z square by 2 dz. Now, you notice that this is an even function. So, you can make it 2 times this term and then again substitute z square by 2 term, and after simplification this term will be evaluated as equal to twice m minus 1 twice m minus 3 and so on 5 3 1 sigma to the power 2 m. In particular, if I substitute m is equal to 1, that is mu 2, that is variance of x, that will be equal to sigma square. So, once again we specify the parameter of the normal distribution, sigma square is denoting actually its variance. So, the parameters mu and sigma square which we use for specifying the probability density function are actually the mean and variance in the case of normal distribution. Now, we can also calculate mu 4 will become equal to 3 sigma to the power 4. Now, let us look at the measures of skewness and kurtosis. So, certainly since odd ordered moments are 0, mu 3 is 0. So, beta 1 is 0 and beta 2 is also equal to 0, because it is 3 sigma to the power 4 divided by sigma to the power 4 minus 3. When we defined the measure of kurtosis or peakedness, we defined it as the mu 4 by mu 2 square minus 3. So, for the normal distribution, the peak is called normal peak. So, if you plot the distribution, it is a symmetric curve around mu. The median is also mu, the mode is also mu, because the highest value is also attained at this point and it is perfectly symmetric around this point. Let us look at the moment generating function of this distribution. So, that is equal to minus infinity to infinity e to the power t x and then 1 by sigma root 2 pi e to the power minus 1 by 2 sigma square x minus mu square dx. Now, this t x term I can adjust with this, and after adjustment this can be simplified, then this turns out to be e to the power mu t plus half sigma square t square. Now, using this one can prove the linearity property of a normal distribution, that if I say y follows a x plus b, then let us consider the moment generating function of y, then it is equal to e to the power b t and moment generating function of x at a t. So, it becomes e to the power b t e to the power a mu t plus half a square sigma square t square, that is equal to e to the power a mu plus b into t plus half sigma square a square t square. So, this is nothing but the moment generating function of a normal distribution with mean a mu plus b and variance a square sigma square. This proves the linearity property of the normal distribution. Linearity property of normal distribution. In fact, this linearity property of normal distribution is valid for several normal distributions also. If I say that, say x 1, x 2, x n are independent and say x I follows normal with mean mu I and variance sigma I square. Then if I consider sigma a I x I plus b I is equal to 1 to n, then that will again have a normal distribution with mean a I mu I plus b I and variance sigma a I square sigma I square. So, and this type of property is true for the normal distribution. Now, let us consider this. If x follows normal mu sigma square, then by linearity property, if I consider x minus mu by sigma, then that will follow normal 0 1. This is called standard normal distribution. This is called standard normal distribution. So, the probability density function of standard normal distribution is phi z. We use this notation 1 by root 2 pi e to the power minus z square pi 2. Naturally, you have phi of minus z is equal to phi of z, and the cumulative distribution function, of standard normal distribution, that is denoted by capital phi of z, that is equal to minus infinity to z small phi t dt, and you have phi of minus z is equal to 1 minus phi of z for all z. So, this is say small phi of z, it achieves maximum at 0, it is symmetric. So, at say minus a and plus a, and if I consider the probability up to this point, this is same as the probability up to this point, beyond this point. So, in any region, symmetric region around 0, suppose I consider minus a to minus b and here a to b, then they will also be same. So, if I consider say the CDF of x, that is the probability of x less than or equal to small x, then that is equal to probability of x minus mu by sigma less than or equal to small x minus mu by sigma. Now, this is nothing but z. So, this is becoming z less than or equal to x minus mu by sigma. So, that is equal to phi of x minus mu by sigma. Therefore, any probability statement of a general normal distribution can be evaluated in terms of the cumulative distribution function of a standard normal random variable. The tables of standard normal distribution are widely available in almost all the textbooks and also the statistical books of statistical tables. The tables of standard normal distribution have been given. Let me explain through some examples here. So, this is the 0, this is your z, this is phi of z. If we consider say minus 3 to 3, minus 2 to 2 and minus 1 to 1, let us consider these 3 points, and we can see here that what is the probability of modulus z less than or equal to 3, that is equal to phi of 3 minus phi of minus 3, that is twice phi of 3 minus 1, that is equal to 0.9974. Because if you look at phi of 3, then from the tables of the normal distribution I will demonstrate here. This is the table of standard normal distribution here. So, on this side they are showing z and on this side phi z is tabulated here. So, if you see 3 corresponding to 3, the value is 0.9987. So, if you see this twice into 0.9987 minus 1, this is equal to 0.9974. That means 99.74% of probability lies between minus 3 to 3. If we convert this to a general normal distribution, this will translate to the statement that in a general normal distribution, 99.74% of observations lie in mu minus 3 sigma to mu plus 3 sigma. So, these were called 3 sigma limits. Okay. Similarly, if we consider modulus z less than or equal to 2, then that is twice phi 2 minus 1, and phi 2 if we see from the tables of the normal distribution, it is 0.9772. So, this is equal to twice into 0.9772 minus 1, that is equal to that is 95.44% of the observations lie in minus 2 to 2 or mu minus 2 sigma to mu plus 2 sigma. Similarly, if I look at z less than or equal to 1, twice phi 1 minus 1, that is equal to twice 0.8413 minus 1, that is equal to that is 68.26% of the probability lies in mu minus sigma to mu plus sigma. So, the normal distribution is heavily concentrated near the mean. Let me do one example here. The specifications for the diameter of the upper end of chalk pieces are set as 3.0 plus minus 0.01 centimeter. The diameter has a normal distribution with mean 3 centimeter and standard deviation 0.005 centimeter. What proportion of chalk pieces will be declared defective? So, the proportion that will be declared defective, that will be given by that it is x is greater than 3.01 or x is less than 2.99, that is 1 minus probability 2.99 less than x less than 3.01. Now, this you can shift to standard normal. Here mu is equal to 3 and sigma is equal to 0.005. So, if you do this, you will get twice minus twice here, that is equal to 1 minus. Now, this probability we just now calculated, that was equal to 0.9 544, that is equal to 0.5640. So, that is 4.56% defective items are there. Now, I give some limiting distributions. So, first result here is that if x follows a binomial NP distribution, if n goes to infinity, p goes to 0 such that NP is equal to lambda, then the distribution of x is approximated by Poisson lambda. Let us prove this. If we consider the distribution of x and that is binomial n p. So, let me consider the moment generating function. It is equal to q plus p e to the power t whole to the power n. This we write as 1 minus p plus p e to the power t whole to the power n. You have n p is equal to lambda. So, we can write p is equal to lambda by n. So, this becomes 1 plus lambda by n e to the power t minus 1 whole to the power n. Here if I take the limit as n tends to infinity, this will go to e to the power lambda e to the power t minus 1, which is MGF of Poisson lambda distribution. This is as n tends to infinity. So, the distribution is approximated by Poisson lambda. I will end up this by two important central limit theorems. One is let x follow binomial n p. As n tends to infinity, the distribution of z, that is equal to x minus n p by root n p q, is approximated by normal 0 1. The proof is, you consider the moment generating function, that is equal to q plus p to the power t to the power n, that we can write as, now consider the moment generating function of z. Now, that is equal to expectation of e to the power t z. So, if you substitute z is equal to this turns out to be e to the power minus root n p by q into t, q plus p e to the power t by root n p q whole to the power n. Now, substitute q is equal to 1 minus p, this becomes e to the power minus root n p by q t and plus n log 1 plus p e to the power t by root n p q minus 1. Now, if n is large enough, then this number is going to be small, because t by that thing. So, and therefore, if that number is small, then this will be closer to 0, that means this number will be less than 1. So, we can consider logarithmic expansion in Taylor series. So, this can be written as e to the power minus root n p by q t plus n. Now, if you expand and apply the formula log 1 plus x is equal to x minus x square by 2 plus x cube by 3 and so on, then this term becomes p. Then so, and moreover, this term will become p t by root n p q plus p t square by n p q 2 times minus p t cube by 6 root it will be 3 n p q cube and so on. This will become minus e to the power x minus x minus x. So, this will become minus, this will become plus and so on. And then you will have yes, this will be 6. What I have done, I have expanded this first, and then you consider minus half and then these terms is square plus and so on. that is equal to e to the power. Now, if you expand this, the first term root n p by q t, this term will cancel with this, you will get e to the power t square by 2 q, because if you consider this p p will cancel out and this n cancels out. So, you get t square by 2 q, and here if you consider the square, you will get p square and by p. So, that p will remain there and then one q is coming here. So, you get here 1 minus this minus t minus half t square by q into p. So, if I take common, this is equal to e to the power and plus terms containing powers of 1 by root n. So, this will converge to e to the power t square by 2, because this term if you take common t square by q 2 q. So, it is becoming 1 minus p, that is q, q cancels out. So, you get e to the power t square by 2, which is MGF of normal 0 1 distribution. That means, if n is large, then binomial distribution can be approximated by a normal distribution after proper standardization. Second central limit theorem, because we have given that binomial distribution also approximates to Poisson. So, there is another one which is called let x follow Poisson lambda. Then as lambda tends to infinity, the distribution of z is equal to x minus lambda by root lambda is approximated by normal 0. These are called de Moivre-Laplace central limit theorems. Actually, the first derivation of the normal distribution was through these limiting approaches only, and then later on it was observed using central limit theorem that if we are considering sums of any independent and identically distributed random variables, then their distributions are approximate. The distribution of the sum as n becomes large becomes approximately normal distribution. So, these and other results we will be taking up in the next class, and plus we will be discussing certain sampling distributions. That means, when we are dealing with several random variables, then what do we talk about?